So you started from September 23, right? Here.
Yes, the program started. Yes.
You're still pretty young. Yeah, enjoy your time. Yeah. So you said your father is in Adno?
Yes.
In which department?
Production.
Okay.
Yeah.
Okay. Yeah, that's the tough part. Yeah. The money is there.
Yeah.
Not in US anymore.
Hey.
Hi, good. How are you?
Good afternoon.
Some don't share, right? Oh, okay. Okay. Yeah. I know. Good mind. Back headings. I don't know why. Probably it's not that why it's not wise to have air conditioning unit at each floor, right? To have a better control, right? It's just it's central. Right?
I think everybody has to learn when they move to the US. You always have to have a sweater when summer and always usually winter. It's always over air conditioned.
Yeah. Hey. You look a bit, man. Yeah. Nice. Yeah. Oh. The name of the program is Master of Science.
Yes.
Just
Research track.
Yeah, I think in Britain there is a Master of Engineering, right?
yeah, in Canada, I got Master of Applied Science. That was the same, yeah. MASC, yeah. That was the. Your Master of Engineering.
Yeah, like the BS, HUS.
It's BS, right? Yeah.
I think that's only in America, in England, they call it VSC.
CSC, I know, yeah, right.
But yes, the American one is.
Name it as it is.
You have a chance to go to the repository of videos that we made.
I did not, no, I have not, but
I think it's helpful, yeah. I guess maybe at some point, I don't know whether, I mean, some of these journals, actually, you can post the video as part of one of the items that is submitted to the paper.
and I think this could be with a little bit of additional things here and there that could be published.
Yes, yeah. Yeah, the experimental data.
Okay.
I think. Okay. Wait for maybe one more minute to respect everyone and we can start. So that's a positive energy for you that one of the examiners mentioned that this is publishable.
Yes, I should, yeah, the outcome, you know.
Okay, let's get started. Good afternoon, everyone. So this is actually my first student's defense kit, which is exciting. I had actually another external student from KIT, just a PhD student. He graduated a month ago. He got the most distinguished award of the university. She was amazing.
No pressure.
This is, Bala is the first student at Pitt, so I'm excited about it. So he is our master student start from September 23, so it's now, getting about 2 years. Graduated from Bala University, Institute of Technology, getting his undergrad, and he's now here for his thesis. So yeah, he did some cool kind of work on kind of CFD of these liquid metals in an extension of what we do in lab. And yeah, the floor is yours. Go for maybe, 30, 35 minutes talk, and then yeah, we'll be follow up with some questions.
Thank you, Dr. Masnadi. Like Dr. Masnadi said, my name is Bala Subramanian, and I will be presenting my thesis on computational fluid dynamics investigation of liquid metal bubble column systems. This research stems from the existing industrial challenge and how I can tackle it with computational modeling. When we are talking about the catalytic system, especially hydrocarbon reactions, there are three main virtues of a catalyst. That is activity, selectivity, and durability. Activity basically means that the catalyst accelerates the reaction. How efficiently can catalyst accelerate the reaction, and selectivity basically means how the catalyst moves the reaction towards our desired product and not undesired byproducts. And durability means the lifespan of a catalyst. So yeah, heterogeneous solid catalyst mainly is contaminated with carbon-rich reaction environments. For example, ethane dehydrogenation, biomass conversion, and plastic recycling all suffer from carbon deposits during the reaction. That is also called as coking. And because of coking, the activity and selectivity is mainly affected, and which ultimately reduces the lifespan of a catalyst. When we now we are going to focus on ethane dehydrogenation. Ethylene is produced via steam cracking. It's one of the major greenhouse gas emissions producer alongside ammonia, and there's an urgent need for coke-resistant stable catalyst to improve process efficiency. Liquid metal emerges as the coke-resistant solution to this problem. Its resilience, it has resilience against coking because the coke that is formed during the reaction is lifted above the liquid metal because of density difference and buoyancy effects, and we can separate the coke out easily. And liquid metal enables catalysis, and it's a continuous operation. We don't have to replace the catalyst as the coke is separated during via buoyancy effects. And liquid metal has high thermal conductivity. It has efficient heat transfer media, and we will be focusing on low melting temperature metals, example bismuth, gallium, and tin. Now, this is the EDH setup in our lab that we are using. This is the FRIT reactor, and FRIT basically means gas distributor at the end of bottom of the column. It acts as a sparger for the gas inlet, and the video shows the ethane bubbling through the bismuth column at 750 degrees Celsius. So the main parameters in EDH we want to observe is bubble size, rise velocity, and residence time. But these are hard to analyze because of challenges of liquid metal. These challenges include opaqueness. Opaqueness limits optical probing. If we focus on the image, the left side is water and right side is liquid metal. We cannot optically see what's happening inside the liquid metal column. And liquid metal has very scarcity of data, hydrodynamic data for liquid metals. And the conventional correlations may not apply. We cannot use cold analogs like water or oil or glycerin to mimic the hydrodynamic same hydrodynamics in the liquid metal column. And the solution is to model a multi-phase hydrodynamics via computational simulation. And the key objectives of my research, there are three key objectives. The first is to examine validity of conventional hydrodynamic diagrams. For example, Grace diagram. I will explain about Grace diagram later during the slide. For liquid metal bubble column systems, to simulate bismuth liquid metal bubble column reactor via CFD, and for EDH, and validate the obtained modeling results against experimental data from our in-house experimental data. And the third objective is to study different liquid metals and focus on how its properties affect bubble column hydrodynamics. Now I will go over the next few slides and explain what are the next few slides coming up in the presentation. First, I will explain about the CFD methodology I've used to model the bubbling system. And the CFD, next, I will show, before we actually do the simulation, we have to validate it against any published data to see if we are whatever we are doing in the simulation is valid or not. I will show the validation against literature reported data. And next, we will move on to simulation of liquid metals after the validation. And we will first qualitatively validate it against hydrodynamic data, like I mentioned before, for example, Grace diagram. Next, we will validate it against our in-house experimental data. And then we will, using CFD, we will compare different liquid metals, bismuth, tin, and gallium. And the key assumption in our CFD is that the flow is incompressible. Both gas and liquid are incompressible. There's no density, there's no change in density over time in the system. And its isothermal condition, we are not solving for energy equation. And there's no reaction involved, chemical reaction involved. And there's no diffusion between phases. There's no mass transfer between gas and liquid phase. And we are going to do a 2D simulation because of computational limitations. And the final assumption is that there's no slip wall condition. Basically means that the velocity at the walls are 0. Now I'll go over the CFD methodology. The CFD package I used is ANSYS Fluent. This is the interface of ANSYS Fluent. First, we create the geometry, then we will mesh the geometry, and we will put in boundary conditions and cell zone conditions in the setup. Then we will go through the solution, and after the running the simulation, we go to CFD post to analyze the results. If you look at the right side image, sorry, I didn't get the laser pointer, but this is the geometry of the image. It's a 20 centimeter reactor. The liquid metal is filled up to 13 centimeters here, and the frit is 2 millimeter at the bottom of the reactor. And this is the meshing I have used. It's a default meshing. I have tried different meshing, hexahedral or orthogonal meshing, and I found that default meshing works fine for our simulation. And the CFD setup, first we have to put in the general settings, such as solver type we have to use. There are two types, pressure-based solvent and density-based solvent. Like I said in the assumptions, since we have no incompressible flow, we are going to use pressure-based solvent, and we are going to do a transient simulation rather than steady-state simulation, because bubbling column cannot truly be a steady state because it's always dynamic. So we are going to do a transient simulation, and we are putting in the gravity. And next step is to choose the multi-phase modeling that we are going to use in the system. There are 4 multi-phase models that we can use: volume of fluid method, mixture model, wet stream model, and Eulerian model. I'm going to use volume of fluid method. I will explain later why. And next is to choose the materials. We have 4 materials: gas, ethane inlet, and 3 liquid metals: bismuth, gallium, and tin. We put in the materials, and we put in the boundary condition. We have 3 boundary condition: inlet condition, outlet condition, and the wall condition. Inlet is a gas flow rate. We use SCCM mostly, standard centimeter cube per minute. And the outlet condition is pressure outlet. We define that the outlet is the gauge pressure is 0 at the outlet. That basically means it's atmospheric pressure. And the no slip condition, that's the wall condition. After putting the boundary condition, we run the simulation. We have to choose the number of time steps and time step size. I'm going to use 0.001 as my time step. I will explain later why. We done a time step sensitivity study and found that this is the time step we are using. And after running the simulation, we are analyzing the results in the CFD post. We can plot graphs, we can plot contour plots, velocity vectors, and XY plots, for example. Next, the multi-phase modeling approach, I used this volume of fluid because volume of fluid captures interface between gas and liquid very accurately, the sharp interfaces, and it's suitable to track the bubble motion in the system, how it evolves in the system. And volume of fluid handles large density and viscosity ratios very well. It's critical in liquid metal systems. And these are the two equations the volume of fluid solves, where alpha is the volume fraction of a phase, and MPQ and MQP are mass transfer between phases. Since we don't have any mass transfer between phases, that term becomes 0, and S is the source term. That is the external field effects if you want to add anything. And the second constraint basically says that in an element, the overall volume fraction is always 1. If you look at the left side image, we see that there are different elements, and the darker region is a bubble and the lighter region is the liquid. We can say that the element that is entirely inside the bubble is volume fraction is always 1, and outside the region is 0. When there is an interface between bubble and liquid in the element, we can the constraint solves it that this is 0.3, this is 0.6, this is 0.3. And that means the 0.3 is the volume fraction of bubble and 0.7 is the volume fraction of liquid. So now that we have been through the methodology, I will go, before we actually do a simulation, we have to do a mesh and time step sensitivity study. For mesh, shows the parameter as bubble to check this bubble rise velocity versus time. I analyze how bubble rise velocity changes with time, how each mesh changes the bubble rise velocity for each mesh. I have tried different meshing element sizes. Elements less than 0.01 crashed, it cannot, the solutions are not converged. If we go less than 0.01, these are the time taken to run each element sizes. We can see that it's almost similar. There's no much variation between the elements. If we go even less than 0.001, the simulation takes days to solve the equation. So I'm choosing the mesh element size as 0.001 size. And same with the time step sensitivity study. I tried different time steps, and we can see that the bubble rise velocity, it's almost same for the different time step sizes, and it doesn't take too long. And the time step size I chose is the second one that takes 1.3 hours. And the main constraint while choosing the time step and mesh sizes, element sizes, is the Coran number. Coran number should be less than 1. That basically assures us that the solution is numerically accurate and there's no diffusion in the system. And Coran number basically means velocity into time step size by element size. The Coran number should be less than 1 for typical simulation. Since you are doing bubble column systems, it should be less than 0.25 to be numerically accurate. Now that we have confirmed the mesh element size study and time step size study, before doing actual liquid metal simulations, we have to validate it against literature. This is the first validation I did. It's a bubble rise velocity in water. It's a 2D geometry. This is a 20 centimeter, 20 millimeter, 100 millimeter geometry, where there is a 4 millimeter bubble placed at the bottom of the reactor from 1 centimeter from the bottom of the reactor, and it's let go. We are going to see how it evolves in the system. We are going to quantify the bubble rise velocity across time for this validation study. These are the results I got. It's plotted between bubble rise velocity versus time. My work is the green line. It matches well with the published experimental method and the CFD method they used in their paper. And there's no curve fitting is applied. So we can say that with confidence that whatever simulation I'm doing matches with the experimental method and the CFD method. And I did one more validation study because this validation doesn't have an inlet dynamics. It's only a bubble rise dynamics. So the next validation study I did is narrow column. It's a 3D model. This is a narrow column with the injection needle of 1 diameter at the bottom of the center for 2 millimeter width, 3 millimeter width, and 5 millimeter width geometries. And the flow rate is 5.7. And this is also a water air system. And here I quantified bubble rise velocity across height of the column for 3 different geometries. These are the results I got for the 3 geometries. For 2 millimeter study, we can my work is between the simulation that is in the paper and the experimental method. And for 3 millimeter experiment study, we can see that my work slightly over predicts the simulation and the experiment from the paper. And for 5 millimeter, slightly under predicts the value, but it's still within the error ranges. The CFD results follow the experimental trends, and we can say that it reinforces accuracy across geometries. Now that we have validated our model, we move on to doing liquid metal simulations. For first liquid metal simulations, I am trying to qualitatively validate our liquid metal simulations across hydrodynamic diagrams. I said before that I will explain Grace diagram. This is a Grace diagram. This diagram predicts the bubble shape based on Reynolds number and Edwards number. It's plotted between Reynolds number on the y-axis and Edwards number on the x-axis. It says that Reynolds number is basically inertial forces versus viscous forces, and Edwards number quantifies for surface tension forces. For each Reynolds number, Edwards number, there's each region for spherical region, wobbling region, ellipsoidal region, and spherical cap regions. We want to check if high density liquid metals, high surface tension liquid metals still follow the predictions made by the Grace diagram. This Grace diagram is plotted using empirical data of basically conventional fluids such as water or oil. These are all. We don't know if it still follows the liquid metal, high density liquid metal systems. So I try to go into each region and try to see if that region follows the predictions made by this diagram. So these are the results I got. We are still matching well within the predictions made by the Grace diagram. For spherical region, we are getting spherical bubbles. And on the right side, I have shown a spherical cap bubble case, and we can see that on the spherical cap bubble still matches with the predictions made by the Grace diagram. So we can with confidence say that the liquid metal high density, high surface tension systems still matches the predictions made by the Grace diagram. Now that we qualitatively validated the shape of the bubbles, we are moving into our actual experimental results. Like I explained before, this is experimental setup in our lab, and we are comparing with our CFD. So this is the CFD result, and with the experimental result, first is the 5-ACCM. I will run the 5-ACCM case. This is the bottom of the reactor. That's a frit, and that's the top of the reactor. We can see that the bubble that is rising in the CFD, it's matching, almost matching well with the experimental at the bottom of the column. We can see small bubbles, and it's almost steady state. There's not much turbulence in the system. Now I'll run the 120 CCM case. We can see that the simulation and experimental are both very turbulent, and we can say that it matches with the CFD that I did with the experiment. There's one interesting thing I observed is that when we run the experiment, there is a circulation in the column. This circulation is caused by, if you watch the video here, as the bubble rises, the liquid metal at the top of the bubble displaces to the bottom to make space for the bubble. This causes a circulation in the system. This circulation, if you look at it at the bottom of the frit, this circulation causes the evolving bubble from the frit to move to the wall. This also contributes to why the bubbles stick to the wall, this circulation effect. And another thing I noticed is when the liquid metal displaces from the top to the bottom from across the bubble, it grazes the bubble and causes breakage in the bubble shape bubbles. If you watch the video, when the liquid metal moves down, the larger bubble breaks into smaller bubbles with the liquid metal and goes down. This is another interesting thing I noticed. Now we will quantify our data. First is the gas holdup analysis. We will compare it with the experimental quantification. So this is a 20 centimeter column that is filled with 13 centimeter liquid metal. It's a pure ethane system at 1 atmospheric pressure and 600 degrees Celsius. And the method to measure the gas holdup is by displacement method. This is after the gas inlet starts to flow. This is before the gas starts to flow in the system. If we measure the difference, that's the amount of gas that's trapped in the system. That's the gas holdup. Gas holdup is basically volume of gas by volume of gas plus volume of liquid. And we can measure the gas holdup using this method. And on the right side, I have plotted gas holdup versus gas flow rates for 3 different flow rates: 5 ACCM, 20 ACCM, and 40 ACCM. We can see that at 40 ACCM, the CFD and experimental gas holdup matches very well. And 20 ACCM, it's slightly higher. At 5 ACCM, it's slightly higher. The 5 ACCM is because when we were doing the experiment without the inlet flow rate, the liquid metal doesn't come above the furnace for us to measure it. I had to look into the furnace to measure the height of the liquid metal, so that causes the disruption slightly in the gas holdup for very low ACCM flow rate. And this again, good agreement observed between CFD and experiment, validating the model's accuracy. Now that we have validated our model across against experiment with our experimental results, we will move on to model different liquid metals and compare the gas holdup. This is gas holdup plotted on the y-axis. We have same gas flow rate for 3 different liquid metals: tin, bismuth, and gallium. We can see that gallium, the green line, has the highest gas holdup, and bismuth has the lowest gas holdup, and tin, the blue line is moderate between gallium and bismuth. This is because gallium shows due to gallium has the low density and high surface tension. If the surface tension is very high, the bubbles cannot break the surface tension at the frit, so it accumulates at the bottom and it becomes large enough to break the surface tension and move to the bubble column. So the bubble size is very high. If the bubble size is high, the gas holdup increases. So because of high surface tension and low density, gallium shows the highest gas holdup and bismuth shows the lowest gas holdup. Now we will compare bubble sizes. This is a plot between bubble sorter mean diameter and flow rate. Sorter mean diameter is a method used for averaging the diameter of the bubbles. We cannot average it directly because the smaller number of bubbles, the smaller number of bubbles in the system is very large, so it reduces the average. We have to eliminate the smaller bubbles and only focus on the larger bubbles to accurately calculate the diameter of the bubble. The formula for sorter mean diameter is summation of each individual bubble cubed by summation of diameter squares. So with this method, I have plotted the bubble size across different flow rates. We can see that again, gallium has the biggest bubble, like I said before. Since gallium has the highest surface tension and low density, it doesn't detach from the frit easily and it starts accumulating at the bottom. Once it becomes large enough, it moves into the system, so the bubble size is very high. And bismuth shows the lowest bubble size. It's because bismuth has higher density. Bismuth has around very large density, so the detachment is easier. If the density is higher, the bubble sizes are smaller and it can detach easily. So the bubble size is lowest in bismuth, and tin is intermediate between bismuth and gallium. Now I will plot total gas in the system versus time. This is the total volume of gas in the system for 5 ACCM, 20 ACCM, and 40 ACCM. For bismuth, gallium, and tin, we can see that at 5 ACCM, there is a very large gas holdup of gallium, again, like before, and bismuth shows the lowest gas holdup and tin is intermediate. And the spikes basically means once gases enter the system, the volume of gas increases, and once the bubble starts to leave, there's a sudden drop, and it starts accumulating again. And once bubble leaves, that's why there's the spikes in the system. And the spikes for gallium is very large compared to bismuth and tin. The spikes in bismuth is very small, the amplitude of spikes. That's because the shape of the bubble is smaller in bismuth when it's leaving. So there's a smaller spikes in the system, and gallium with the large bubble size shows the larger spikes. If we look at the 40 SCCM case, there is a special case of gallium where the gas in the system is very large, and it reaches and it drops again around 7 seconds. I will explain why the gallium special case happens. If we look at the video here, you can see that gallium entirely pushes the liquid metal out of up before it still cannot form a bubble. It cannot break the surface tension in the system. So it entirely pushes the liquid metal up. And at around, once it reaches around 6 seconds, that's a bubble formation here. And after, when it's 6.5 seconds, when the larger bubble leaves, then it reaches a steady state. So we can see that it reaches a steady state. This is because of, again, like I said before, high surface tension of the gallium and low density. Because of low density, the entire gallium system is being pushed up, and then there's an instability in the system, and bubble starts to form, and it reaches steady state. Now I will plot the same data for bismuth, tin, and gallium at different flow rates: 5 SCM, 20 SCM, 40 SCM. If we look at the bismuth case, the spikes, the green line, the spikes in the bismuth case for 40 SCM is very large compared to tin, where the spikes in the tin case is very small. But when I said, so basically the spikes means the gas is leaving the system. So when the spike, when the gas leaves the system, there's a drop in the spike, and gas accumulates in the system, spike increases. And the amplitude in the bismuth is very large compared to tin. This contradicts what we did in the bubble size analysis. We found that tin has the intermediate bubble size and bismuth has the lowest bubble size. But if we analyze from total gas in the system here for 40 SCM case, the bismuth shows the larger bubbles leaving the column, and tin shows a smaller bubbles amplitudes leaving the column, and larger number of bubbles in the system. We will look at why it's the case. If we look at this video for bismuth and tin, if you see the bismuth case, the bismuth, because of shorter detachment time and smaller bubble sizes, it rises faster due to larger density difference. Bismuth has the highest density, so it rises quicker than in the tin case, and it coalesces around the top of the column. Even though the bubble size is smaller, but once it reaches the top, it coalesces into a bigger bubble and it leaves the column. That's why there's a larger spike in the bismuth case, even though there's a smaller size. And for tin, if you look at the tin case, there's not much coalescence in the system because the rise velocity in the bismuth case is lower compared to tin. So there's not much coalescence in the system compared to bismuth. And there's a larger number of gases leaving the system compared to bismuth. Now we will look at bubble rise velocity. This is plotted between average rise velocity versus time. We can see for 20 SCM and 40 SCM case, we can see that bismuth's rise velocity is highest compared to tin, and gallium shows the lowest average rise velocity in the system. Like I said before, since bismuth has a lower size of a bubble, it rises faster in the system. And since gallium has the highest bubble size, it rises slower in the system. So same for the 40 SCM case, but again, gallium shows a deviation from the bismuth and tin. Again, that is because the slower detachment time of the gallium in the system. Now that we have analyzed the velocity profile in the system, we will look at another interesting thing, that's the splashing in the column. We can observe splashing at the top of the liquid metal once gases, if you look at the image, there is 5 SCM, 20 SCM case, 40 and 120 SCM case. At 5 SCCM case, both experimental and CFD shows us very small splashing in the system. Yeah, but for 20 SCCM case, it's larger than the splashing is worse than 5 SCCM case, but it's not as worse as 40 SCCM case. And 120 SCCM case, the splashing is so worse, it starts to solidify at the top of the column and it doesn't come back down. Why we are focusing on the splashing is because if there's a splashing and the liquid metal solidifies at the top of the column, there's a liquid metal loss in the system, which could lead to contamination. And because of the solidification at the top, the gases in the system cannot escape and it's trapped inside. So it's important for design to find the liquid metal loss because of splashing and contamination. Another parameter I quantified is pressure drop. This is plotted between gauge pressure and height for three different liquid metals, bismuth, gallium, and tin. We can see that bismuth has the highest pressure drop, and tin shows intermediate, and gallium shows the lowest pressure drop. That is because pressure drop only depends on density of the liquid metal. I try to increase the flow rate in the system to see how pressure drop is affected. But irrespective of how I increase the flow rate, the pressure drop remained constant across the system. So it only depends on the density of the liquid. And since bismuth has highest density, it shows highest pressure drop in the system. We come to conclusion, Charot. The conventional hydrodynamic diagrams could cover bubble shape behavior of liquid metal systems. We did that with the Grace diagram validation. We can say that hydrodynamic diagrams still satisfy the high density, high surface tension liquid metal systems. And the CFD simulation is a powerful tool for categorizing bubble dynamics, bubble column hydrodynamics in ethane dehydrogenation in bismuth liquid metal column. We can infer that gas holdup is strongly influenced by density, and bubble shape is primarily affected by surface tension, and bubble size and detachment is primarily affected by viscosity, and hydrodynamic behavior varies significantly based on different properties of liquid metals. We can see that viscosity affects bubble breakup, and size, surface tension affects shape and instability in the system, and density determines the buoyancy and lift forces in the system. And overall, this study provides a foundation for reactor design and scale up in liquid metal column. And for future work, we suggest that 3D modeling for a full-scale reactor is recommended, because when we are doing a 2D model, the bubble only moves between two directions. We cannot accurately track how the bubble moves in a 3D domain. We can do that with a 3D model. And since the next suggestion for future work is to solve the energy equation and find how temperature affects the column, and add kinetics to see that species transport in the system. I would like to express my sincere gratitude to Dr. Mohammad Masnadi for his invaluable guidance and support. And I thank my committee members, Dr. Veser and Dr. Hseen Baled, for their insightful feedback and encouragement. I am grateful for the Liquid Metal Research Group, Aditya and Aime. I'm thankful for them. And I acknowledge CRC for providing the essential resources for computational modeling. I thank my friends and family whose patience and encouragement kept me going. Thank you.
Well, thanks very much. Question from the audience? Yeah, anything else?
Yeah, nice talk. You work in develop and you've also done simulations. So what parameters would you recommend for experimentalists to try to optimize the lab this field?
What parameters I would recommend to optimize?
Yeah, for experimentalists, like people in the lab and same experiment, what should they look out for?
That's a great question. We can optimize temperatures to see how different temperatures affect the liquid metal, but that depends on the sensitivity and conversion rates. Parameter I can recommend optimize. I'm not sure. I will think about it, but I mainly do CFD, so. Yeah.
Just wanted to ask, when you listed about the splashing,
Mhm.
and you were giving particular flow rate, I believe in cubic centimeters.
Yes.
Does it matter how wide the column is?
Yes, yes,
Yeah,
yes.
okay.
Yeah.
Just
So-
wanted to confirm I understood the
Uh-huh. Yeah.
genetics properly.
So if we want, I try to find the dimensionless numbers to see if how splashing affects irrespective of the size of the reactor. Since I'm using a very small 13 centimeter reactor, the splashing is worse here. I try to do find how dimensionlessly we can model a reactor here, but that depends on the Weber number, and I'm not focusing on the, yeah.
Thank you.
Mm.
Thank you.
It's not scientific, but since you have worked on these, like if another student was to come and take these, what do you think has been the most challenging part to get you going and basically learning your own? Like for a new student who wanna do or replicate what you are doing, what are the things you tell them to watch out for so that their learning can be fast?
So when I started my work, I faced challenges with the CFD software package. I struggled to learn how Fluent works, and whenever I run a simulation, it crashed. The solution does not converge. So I suggest they take a CFD course before doing actual simulations, and yeah.
But how did you resolve the crashes? Well, did you take any systematic way to?
So there are forums on the online. If you are getting error in the simulation, we can analyze why the error is happening. Most of the error is due to the current number. As I said before, the solution does not converge because the current number is not less than 0.25. It's very over. It's like going thousands. So to decrease the current number, we can see in the formula that it's velocity versus time step size by element size. If we go to very smaller time steps and element sizes, most of the problem solves. But that again increases the computational time required to solve the problem. So first, before doing simulation, we have to find the element size, optimized element size, and time step size by doing a sensitivity study.
That
Then
sensitivity analysis helps to
Yeah.
reduce the number of failures.
Yeah.
Any other questions?
Yeah, I'm just curious, you try to model an alloy of the liquid metal and achieve that because I noticed all your models are based on single metals.
Yeah. We could easily model a alloy. So bismuth, tin, and gallium, it's not in the Fluent package. I had to create it manually. I put in the density, the surface tension value, the specific values. So if we have the data for each alloy you want to model, we can just define the properties of the alloy and easily model it using the properties we have. And finding the properties may be a bit difficult at the temperatures we want. At 600, 700 degrees Celsius, there's limited data of properties for alloys.
Questions?
Maybe my last question.
You're asking good questions, yeah. You might be able to stay here.
Yeah, I think go back to the validation too.
Yes.
Yeah, so I noticed your model is 2D, let's say 3D.
Yes.
Validating a 2D model against 3D, like you making assumptions.
No. I did a 3D modeling here. That is my model.
Okay, so your validation here is the only 3D simulation.
Yes. All my other simulation are 2D. I chose this specific paper to model is because since our experimental model is constrained by wall effects, it's dominated by wall effects. I chose this geometry because it also has very large number of wall effects. So to see if whatever simulation I'm doing is still valid in this wall effect affecting that geometries. So that's why I chose this 3D geometry. And it has both literature data and their simulation data in the paper that I can validate it against. Yeah.
If there's no other questions, just feel free to get a donut. They're dining there, and yeah. So we ask you to leave the room and Yeah, we keep going. Perfect. Hey, very much. Maybe, yeah, Steve, you might want to start.
I think, the focus. No, please, I mean, I've been part of the discussions the whole time.
Anytime.
Oh, you're okay, I'm still remember.
I have a lot of questions.
So,
Okay, I'll start with by the way, great work,
Thank you.
great presentation. So very nice, although I can tell although you did work. So I'll start with the assumptions
Okay.
to model.
Yeah.
So definitely I can't criticize any of these assumptions because the validation of those is excellent, you know.
Thank you.
So, now you assume that the temperature is constant,
Yes, we are not solving for energy equation.
right?
Yes.
And also there is no reaction.
No.
So there is no reaction.
Yes.
Source also included in your model.
Yeah,
Right?
it's not.
Okay. Now, the whole purpose of your work,
Mhm.
right, is to better, you know, optimize the operating conditions of for the reaction.
Yes.
The hydrogenation of ethane
Mhm.
or
Yeah.
process of ethane, right? So, and we know how these reactions are, you know, endothermic, right? So the temperature will change, right?
Yeah.
And so was it difficult also to include, you know, like heat source in the model?
No, initially I was solving for energy equation,
Yeah.
but the computational time takes us very longer and I'm not quantifying how temperature changes. I was doing it initially, but we were not interested in how, since the cold gas is coming in a hotter liquid, how the bubble, the temperature affects the bubble in the column, but we were not interested in how it affects.
And how about the reaction? So did you try also to include, even if it's just symbol, you know, Arrhenius term,
Yeah.
you know, in your model?
Yeah, no, I didn't add any species transport. I didn't model any mass transfer mechanisms, chip mass, yeah, in the mechanism in the system.
Okay, okay, but this is, I see that you put it also as a future work, you know, which is, yeah. So, okay. And the other thing is that for the validation, so you did the validation based on, just for this one, right?
No,
The validation, your model, you compared it to experiment.
yeah, that's just bismuth. Yes.
Yeah. Do you think it's sufficient also to do that and then just also transfer them, also use the model also for different
To validate it
Yeah,
against different
yeah.
liquid metals.
Yeah. I mean, how confident are you, you know, in the data that you got also for tin and for gallium? Because you don't have experimental data to compare that, the results with, right?
If you're asking about my CFD confidence,
Yes.
I did 2 more validations with published data, but I only did bismuth for our in-house validation. I could have done more validation, but our PhD student said this already cost $100 to do this validation. So
And did you check if there's any available detection data other on the other liquid minerals? And that you can compare your, you know.
I did see,
Your results with.
yes, I did see liquid metal simulations in the literature, but there were not any straightforward CFD used in the literature. There was one paper with mercury systems, but they had external field effects like magneto-hydrodynamics effects. So we didn't focus on external field effects, so I couldn't validate against the paper. I found there was limited data on liquid metal simulations where I can validate it against.
Okay.
Yeah.
Can you show me the blood, the mass blood, like this?
Yeah.
Yeah, this here. So based on your study,
Yes.
what shape of bubbles you want to have, during the reactions?
Ideally, if we have a smaller bubbles with spherical shape, which can increase the surface area because the reactions happens at the surface of the bubbles, that would be ideal. So I would say the spherical shape is ideal for reactions.
Spherical shape,
Yes.
because of the stability or?
Spherical is more stable. Yeah.
But don't you think that, the spherical cap, they have larger?
Yeah. So, but for spherical cap bubbles, we have to go for higher flow rates. But if we increase the flow rate, we can get spherical spherical cap bubbles. But the residence time decreases because it's like a bullet that enters and forms spherical cap bubble and leaves immediately. If we want to increase the residence time in the system, we have to go for a stable spherical bubble.
Why do you think the residence time will, well, you need to have a better, higher residence time or lower residence time for engage?
I would think it's higher residence time.
Maybe, right?
Yeah, I think so. Yeah.
Should we have a kind of an optimal residence time? You give a lot of time to your reactants and some of your products, they might get further converted to something that you
byproducts.
don't
Yeah.
like.
So we don't actually know the mechanism that happens inside the liquid metal system. We don't know how the reaction takes place. But if we go over a certain limit, yeah, the byproducts, coke formation can be very high if the residence time is very high. Yeah.
So this goes back to the Cornelius maybe question that what kind of messages for in terms of optimization of your system you want to get out of these?
That's a little bit, I mean, it's a nice thesis, but I felt that was a little bit missing at the end, but I mean, say make the correct question in the beginning. I mean, all of this is, of course, setting the model up to describe our reactive case. That's what we're interested in, and it's perfectly fine that, again, you set up the basic model here and putting the energy balance and reactions, it will dramatically increase the stiffness of the equations and will take much longer time. But it would have been really adding a lot of value, and if you can consider that to add maybe one paragraph at the very end where you just make some conclusions, right? I mean, keeping in mind this is generally meant as a pre-study for catalytic systems, reactive systems here. What can you conclude? Right? You want to optimize or maximize the gas surface interfacial area. What can I conclude? Where should I operate? I may in some cases want to maximize the residence time. How would I achieve this? In other cases, you want to have a really short residence time or optimum. So really put it a little bit more into this context, even though you have done it, but you can actually draw some really helpful conclusions about it from the results.
From my study, from the hydrodynamic study, I would recommend the bismuth liquid metal as doing for the reaction systems because bismuth produces smaller number of bubbles and it's optimal for the rise velocity. It's not very high. It's very high, but I would say bismuth is perfect for using for reaction, but
it's going in the right direction, but what I would recommend is that's almost a little bit jumping too far, the recommendation, right? Because, hey, ultimately we're talking about catalysis, and bismuth might just not do the catalysis for you. You rather want to make a recommendation. I would recommend a high density liquid metal which among those might be bismuth, but once we go to alloys or whatnot, it might change into things. Try to sort of make robust qualitative recommendations rather than these highly specific ones.
Yeah. Yeah, since larger, higher density liquid metals produces smaller, smaller size bubbles, we can say that we can recommend higher density liquid metals for reactions. I can conclude.
I guess you can also comment on the geometry and wall effect. That's really huge, right?
Yeah.
I mean, really disturbs everything from the scratch, from the beginning, right? And I know that you already have done wider reactor simulations to show part of the, it's not included in your thesis.
Yeah.
But I agree that there should be few paragraphs of conclusion on relevance.
Even a single paragraph with sort of a few, I think, I mean, you have a lot of assumptions here which may raise questions about some conclusions, but there are some that I think you can make very robustly from this. So really extracting that, I think would have a lot of value.
Also, what things should be also considered when scale up of the, the setup for
To scale up the this hydrodynamics, we have to look at again wall effects. Since this is dominated by wall effects, if we scale up the column size, there won't be as much wall effects as this, and we can scale up the reaction. Yeah, we can scale up the column. Do you have a question in the?
No, this is, I'm just saying that this is something that we can add also.
Okay.
Yeah.
Yes,
It's
that's
more about,
what learnings can help for scaling or, I mean, designing actually, right? You might just want to think about the horizontal configuration.
Yeah.
Right, now that you understand these vertical kind of the reactors has these issues that might be, or how they can be addressed. One kind of configuration, so.
Yeah. How we can go for rather than a straight vertical column, like this shape.
I don't think you want to get into that business, but you can think about, yes, comment on geometry of your reactor is important because of what you're observing, right?
Yeah. And I tried different inlet geometries for the Grace diagram validation. I did a single inlet. I didn't use a frit. So I tried 2 inlets, 4 inlets. So I can say that frit is better to use compared to single inlet for the reactions.
Again, I would be careful with this is better, right? What is better ultimately depends on what I want to achieve. So rather make a statement, if you go from individual inlets to a frit, then this will result. And then it's up to the user or the reader to decide is that good. And you could add a statement which might be beneficial if this is desired.
Yeah.
Right? But don't try to avoid to jump to conclusions that already say like, I know exactly what you want. No, you may not know what I want. Right? I mean, you maybe don't think about a totally different reaction system that would have in mind.
Yeah, the other thing is that you showed the hydrostatic pressure.
Yeah.
Right?
The pressure drop in the column.
Yeah. What's the main, what do you want to show with this here exactly? So this is just because of the density difference, right?
Yes. What I was trying to achieve was to see how flow rates, increasing the gas injection flow rate, will it affect the pressure drop in the system? I was trying to analyze that, but I went as high as 120 ACCM case, but the pressure drop didn't change irrespective of how my gas inlet flow rate is. So it doesn't depend on the injection flow rate, it only depends on density of the liquid.
So did you see if I'm not a CFD expert, but so is there any way to investigate also the pressure across the bubbles?
Yeah.
Pressure drop.
So I did try to find the pressure inside the bubble.
Yeah.
It depends on surface tension and the length and width of the bubble. Yeah. So
Because that would be more important than this.
yeah. I,
This is ultimately, when I went through this, and actually did the quick calculation. I can draw this line with pen and pencil. All I need is the density of the metal and I can draw the line.
Yeah.
So, but Hseen's point is exactly right, but it would be really interesting to know how does the bubble pressure, the gas pressure inside the bubble change from the bottom to the top of the column? How does it change with the size of the bubble,
Yeah.
bubble, things like that? Because that obviously again goes back to our interest in using that as a reactive environment.
I did try to model a single bubble and see how temperature once the gas enters the system, how temperature goes into the bubble, how long does it take, how pressure affects the system inside the bubble. But I didn't fully go through.
You can easily probe that, right?
Yeah.
For the bubble pressure,
Mhm.
you can easily probe that and we can characterize it, right? So.
And when I looked at the equation for the pressure inside the bubble, it's surface tension into 1 by R1, that is the vertical length and horizontal length, 1 by R1 plus 1 by R2. I don't think it depends on the density of the.
But that's when you want to compute it. If you want the simulation solves for pressure, right?
Mhm.
So you can take directly the pressure out of the bubble
Yeah.
that you're basically
Yeah.
simulating,
Mhm.
right? I think that's what is needed here to already solve for your product column.
Mhm.
And you can characterize based on different, especially based on different liquid metals, as you said, the surface tension will impact the
Yeah.
pressure of your bubble. So yeah, I think that's an excellent comment.
Another comment I have is about the flow rates. So the maximum flow rate that you use is 40, right? Or
Yes,
yeah.
for
So-
comparison between different metals, maximum flow rate is 40. Yes.
Okay, so is this reasonable? Or this is the flow rate for when it comes to industrial scale or not?
Yeah. When we were doing, when he's the one who does this experimentally, he only goes up to 20 SCCM in the case. He doesn't go above 20 SCCM because that's the residence time drops very high with the increase in flow rate. He analyzes 5, 10, 15 and 20 SCCM. He doesn't go beyond 20 SCCM in the experimental case. So I stopped at 40 SCCM.
And then you showed also nice transient plots, right? So at the end of your, can you show these plots also for the different metals and also for different rates?
You mean the
Transient.
the velocity plots,
Go.
gas holder?
Yeah.
Okay.
Yeah. Did you try, I don't know if, because here you're changing also you're changing so this is the gas, also the calculating out the gas hold up also for different flow rates, right?
Yes.
Different conditions.
Yes.
and
Yes.
Different, did you try also to generate, also to study the gas hold up also as as a function of dimensionless numbers like Reynolds number or, But that would, because that way maybe you can generalize it also for other metals, not only for these three, would that help, you think?
I mean, we can, if you do more work, we can try to find a empirical correlation between different properties, density, surface tension, and correlation, gas holder equations. I don't think we can totally generalize it. We can only do a case specific dimensionless number quantification for gas holder to make a general gas holder equation. I don't think it would be difficult.
And discuss, I mean, I think this is interesting, and this is something you didn't quite discuss enough, honestly. I think the difference here between bismuth and tin, right? Tell me a little bit more what you see.
Okay, so when I was discussing the bubble sizes, we found that bismuth has the smallest bubble size and tin has intermediate and gallium has highest bubble size. But when we look at the gas in the system, how it moves in how transient behavior it has. We can see that bismuth has bismuth leaving the system, that's the drops are very large. That is not that's not how it's supposed to be, because the bubble sizes are small. If the bubbles leave the system, it should be a smaller bubbles like those. But we see a contradictory behavior where the bubbles leaving the system are very large. And when I looked at the video, I found out that even though the bubbles are smaller, as it rises to the top, since the bubbles are smaller and bismuth has a very high density difference with the gas, that's a very large coalescence happening in the column. Since it's rising so fast, it coalesces to a bigger bubble at the top before leaving. So that's why there is a bigger drop in the spikes amplitudes in the system.
Yes, but I mean, let's start with the tin system.
Yes.
What do you see very systematically here? If in your graph, you go from 5 to 20 to 40.
In the graph,
Yeah,
14.
what changes? I mean, other than the total gas hold, well, the average gas hold that, but what? Man, I put out how to ask the question without giving you the answer implicitly, but what stays the same and what changes as you increase the flow rate?
what stays the same?
I mean, you have basically two characteristics for these curves, right?
There is frequency of the gases leaving the system and the size of the gases leaving the system.
Yeah, exactly.
And from 5 SCM to 40 SCM, when we increase, the frequency drops. Frequency increases because 5 SCM is very small bubbles, and it takes longer to form bubbles. But for 40 SCM case, the bubbles leaving the systems are very rapid, so there's a larger number of bubbles leaving the system.
Frequency increases, which means I have more bubbles per unit time.
Yes.
What is the amplitude corresponding to?
The amplitude stays the same.
Right, and what does the amplitude represent here?
The size of the gas bubble,
Right.
it
So
stays the
in
same.
tin, you see actually a very interesting effect, right?
Yeah.
It seems like increasing the flow rate does not change the bubble size. All you do is you're creating the bubbles with higher frequency and then the bubble out.
Yeah, there's no coalescence
Now, let's
between.
go to bismuth.
Since there's no coalescence in the tin, that's why it doesn't change. But bismuth has a very large coalescence amount. Since the rise velocity is higher, it coalesces into a larger bubble. That's why the amplitude is very large. But
That's not all you see, right? I mean, if you look at the 40 SCCM curve, other than seeing these very large spikes, what else do you see?
there's a very less number of bubbles leaving compared to 20 and 5 SCM case in the 40 SCM case for bismuth.
True, which is almost necessarily the case because you form these large bubbles, but what else is really jumping out? I mean, it becomes very irregular. Before they are all more or less the same. Now you have small bubbles, huge bubble, intermediate sized bubbles. It's really interesting, right? Why?
So when I observed the simulations, I saw that once bubble starts to form and it starts to coalescence, it becomes a larger bubble and leaves. And the next bubble doesn't coalescence large enough at the same size as the previous bubble. It stays relatively small and leaves the system. And the next bubble coalescence again into a bigger bubble.
Right, but there is something else, but why don't you run this model?
Yeah.
For this man. What else do you note here? Quite pronounced.
The coalescence is.
You see also a lot of these larger bubbles, they're starting to carve little bubbles, right? They spit out little bubbles.
The bubble breakage.
Break off. Right? Like, where does that break off come from?
So because of high viscosity in the system. So when the high viscous liquid metal moves from the top of the bubble, displaces to the bottom, it applies stress shear to the bubbles.
Shear, exactly. That's what I was talking about, right? The shear force effect there, I meant the viscosity, right? So it points you again to the importance of viscosity in these systems, right? So I think that could have come out a little bit more clear in the discussion, right? Because it's really a striking effect when you look at these graphs.
I made a script for 45 minutes, but I kept missing details that I wanted to explain and finished it at
Yeah.
35. I don't know.
I have actually one observation here. So if you go to gallium, I have a question there for you. I was just thinking about it during. Okay, so do you expect this behavior to continue, or it's gonna just go stable after, let's say, after 10 seconds? If you keep simulating this, are you gonna be in a now similar to bismuth and tin forever? Or this phenomena can start to take place again? And the other question that why if it's not gonna happen again, what's the reason? Because
Okay.
you still have the same, what's happening here? Yeah,
So-
I'm curious to see this for 30 seconds.
Yeah.
And then,
I it's actually the same question, just sort of flipped around a little bit. Why does this happen?
So,
So you're pushing that liquid up
Mhm.
continuously. And
uh,
at some point it suddenly decides like, I'm done. And the bubble breaks off.
so there are two reasons I can think of for this to happen. The first reason is so why this is happening is because gallium has the lowest density and it's basically being pushed up easily compared to bismuth and tin. And why is this happening is because the surface tension is very large. So for the bubble to break into the surface tension, it has to accumulate enough pressure in the gas gas phase to break the surface tension of the liquid metal, and the bubble starts to form. And once the surface tension is broken, it reaches steady state. I don't think it will repeat again. It's already broken the surface tension. It doesn't have to be happen again. And the other reason is because
Let me just jump in here. What makes you think that you need to build up more pressure as you push that column up higher and higher?
so since we are using a frit, the force pushing the gas, it's equal across from left to right. There's no gap in the force where the liquid metal can flow behind to form a bubble. Since it's equally pushing everything up, that's why the liquid metal is being pushed. But there is a slight instability in the system where there can happen error where this side is not equal to this side, and this side moves the bubble up and the liquid metal flows
what
down.
causes that?
Anything can cause that instability, but
Example what? Experimentally and numerically.
experimentally, I would assume that the oven doesn't eat everything thoroughly across the system. One side eats higher and one side eats
So
slow.
you don't have perfectly symmetrical
Yeah.
characteristics.
So the properties are not exactly symmetrical across the interface. There can be
But how about here? Here, you assume everything is symmetrical. Then what causes that instability?
the error in the system can cause an instability.
What error?
I think when we are solving the equation, there can happen a numerical diffusion in the system where we are not accurately solving the equation across different elements in the system. One element gives out the error in the system, and the liquid metal flows through that element.
Basically numerical inaccuracy.
Yes.
Yeah. So with that now back to Dr. Masnadi's question. Do you expect that to happen again? If you ran this another 10 seconds or another minute?
Yeah.
You expect to see another big bubble like that?
I don't think that can happen. If you are looking at this snapshot, there's already a gas bubble forming here. As the next bubble leaves the system, there's a bubble already forming. So there is no pushing of the system exactly as the symmetrical system. There's already one bubble forming at the bottom as the bubble starts to leave. So I don't think it can repeat again. If we stop the flow,
I have the perfect.
Yes.
Frontal interface.
Yeah.
But you already have a deformation in there, and therefore you can never have this. This is a very interesting, but a pure transient initial instability.
Yes.
Do you have the same any other follow-ups? Or,
No, that's not.
okay.
Any other questions or?
Yeah, so I do have other.
Go ahead, yeah, that's free then.
Okay, so this is probably not exactly related to your CFD study, but it's the experimental setup. So in that, I don't know if you are you familiar with the setup?
Yes, I run the experiment for validating against my model.
Okay,
Mhm.
so on the top of the column,
Mhm.
is this, do you have, what do you have there? Is it inert, gas like nitrogen, or is it air or what?
When I was doing the experiment for my validation, we first let the gas flow into the system and leave the system, and there's a cotton at the top to block the system, and it goes into the mass spectrometry. So I think we already have ethane in the system that's all about the top. So that's what we have. I don't think there's nitrogen in the system.
So it's then, are you saying that you flush it with
Ethane, yes,
with
before.
ethane,
Mhm.
so you have the pure ethane?
Yes.
Okay, because I wasn't sure if there's air, there could initiate oxidation, right?
Yeah.
Yeah,
Okay.
so I'm just.
You cannot have air in the system.
Yeah. So, and then you mentioned also in the study, in your thesis, that, so when you take the videos, you take out the column very rapidly, right, very fast, out of the furnace, and take the videos, right?
I'm sorry, can you repeat the question?
So when we take also when you record the video,
Yes.
right?
Mhm.
So you take also the column out of the furnace.
No.
Or how do you take the? Yeah.
So I chose to validate against 13 centimeter because that's the height of the furnace we have. So that's exactly the height of the furnace. So we heat up accurately 13 centimeters, and we move the liquid furnace up and down to see the bottom and the top. We cannot fully take the furnace out of the system. It cools down rapidly, and so we just move the furnace up and down to see bottom and top.
And this wouldn't change the temperature? There won't be any temperature change?
That would be cooling effect, but I don't think it's that rapid enough to cause any irregularities in the system. We just take a video and put it back
There's
immediately.
no other way.
What helps you with the cooling effect? Why? I mean, clearly, of course, you move the oven down, heating anywhere up there, it will have some effect on temperature. But why is that effect dampened compared to sort of a conventional fixed bed reactor, for example?
The heating effect, why heating effect is dampened in the system?
Right,
You mean-
why does the temperature not drop as drastically when you move the oven down?
The excellent heat transfer in the system, the liquid metal has high heat transfer coefficient. So even though we are heating only the top of the liquid metal, the heat travels down faster. Mhm.
One of the reasons why we're interested in liquid metals, because they have such huge heat capacity and the conduction that we expect that we get generally very uniform reaction conditions in the systems.
Now I have another question. So, I teach also process design with the seniors, and I use also styrene production using the dehydrogenation of ethyl benzene. It's a catalytic reaction using also iron oxide, potassium bromolyl iron oxide. Do you think this also there's a major challenge also in the industrially, because of the cooking formation, and the catalyst also gets deactivated because of the progress of the coke. So do you think also this can also the concept of similar to the liquid metals also catalysis here can be also transferred to something like that also? The production of styrene using the potassium from all the iron side. If it's melted,
I would think liquid metal still can act as a catalyst for the reaction, since we can avoid coke formation. But I have to study the mechanism to find if
This is probably.
Well, the problem with metal oxide, of course, is that now you're talking about melting points that are crazy, right? I mean, you're talking about going to 1,000 degrees or so. So how do we, what does a reactor look like in which you would do something like that? I mean, there is sort of, I mean, I've been talking quite a bit also about this with folks at Braskem and whatnot, and we discussed at that point that it might be interesting to actually use a little bit of metal oxide. So you basically would have like a molten metal with little clusters of metal oxide moving around in there. Those clusters will be solid, but they might still do analysis. So again, eventually I would love to get there, right? I mean, these mixed systems where you have solid catalyst and liquid metal combined, but that is a challenge.
Yeah. You want to?
Sure, yeah, I mean, let me, but we touched already on most of the questions that I had. But one that I'm actually really struggling with, slide 23. You have these CFD relations here with your flow speeds.
yes.
Can you explain again, what are you showing here? What's the velocity that you're showing?
So since the gas is rising, it has to displace the liquid metal from the top to the bottom. It moves up, it moves across the bubble and goes down. This causes a circulation in the system, and this circulation is interesting because we assume that the bubble rise velocity inside the bubble is constant, but since when I plotted the velocity vectors, the velocity inside the bubble are not always constant. There are different rise velocities in the system. And
that's basically what I'm getting to. I'm a little confused at what I'm looking at. I can easily understand the flow pattern in the liquid, but it seems like your flow pattern is almost unbroken with like a little bit of wiggle as you go from the liquid to the gas phase. I would have expected that the gas inside the bubble has its own dynamics that has virtually nothing to do with the flow in the liquid phase. So I don't quite understand why there is so little difference. Why is that how can all the gas in the bubble flow upwards? I mean, if you have flow in the bubble, you would have to have a
circulation inside the bubble.
Circulation inside the bubble, and your flow field doesn't seem to show that. I don't understand. I'm not sure your flow field is correct, or at least I can't make sense of it at all. I mean, again, speaking purely inside the bubble, the outside in the liquid, that makes perfect sense. That's clear.
What are these vectors exactly?
Velocity vectors,
These
the
are
direction,
vectors,
yes. So
And the velocity, again, sort of these are from fluid, right? Fluid spits those out.
yes.
So it's the velocity of what? Because again, to me, also, I think if I show a velocity vector, I mean, I would have a velocity vector field for my liquid, and I have completely different velocity vector field for my gas. So is fluid just saying, like, I don't care whether it's liquid or gas, it's the velocity of whatever I have here? Or
Yeah.
How does it come?
So I don't think this shows independent velocity vectors for gas and liquid. This just shows how each element in the system, how its next step is going to be, where's the velocity direction is. That's what it's showing. And to answer the question why there is no circulation inside the bubble, I don't think this is large enough bubble to cause a circulation. This is a very small reactor, small bubble. So all the directions of the velocity vector are in unison. So if we have a large enough bubble, we can fully see I think that can be a circulation inside the bubble if the bubble is large enough.
So when I zoom in on these bubbles, if you look at the vectors, you see a little bit of, I mean, everything looks upward, but they're not all in the same direction, okay? And I agree, I assume these are not that large bubbles to create that fully developed circulation. That's what what I'm guessing. But you can check it. You can
Yeah, yeah.
create a large bubble, to see if you observe.
Mhm.
You should observe, I agree, yeah.
And again, I mean, I'm asking this also, I mean, number one, because again, I don't understand it, number two, because it really, this is critically important, right? Because if we have catalysis happening here, we really need to understand what is the gas flow pattern from the core of the bubble to the wall, to the interface and back. And some sort of recirculation would be extremely helpful.
I see.
Get good contact.
So in that sense, you're saying if the cost of having recirculation is to have a larger bubble, then there's a trade-off between having a smaller bubble.
It becomes an interesting question,
Right.
ultimately, right? I mean, if then you may have actually sort of two optimal situations with a suboptimal in between. Really small bubbles, so that actually diffusional transport is perfectly efficient to get the exchange. And really large bubbles, where now I actually get eternal convection
Mhm.
cycles that help me with the mixing, and in between I have bubbles that really don't work well.
Mhm.
I could actually make for a really interesting consideration.
That's super interesting.
Even though I don't think recirculation inside the bubble is as much beneficial as you think. As the bubble surface, it's the liquid metal. I think it pushes the liquid metal out of the way and it goes down again, and the next gas in the system touches the liquid metal. So even we don't have to be there will be I think all the gas molecules in the bubble touches the liquid metal at least once, so the reaction can take place. I don't think there will be a gas inside the bubble that doesn't react at all and leaves the system.
Well, but again, this is exactly what I would have expected here, but what your flow field does not support, right? I would have expected to see that there is gas that is pushing up towards the interface, and then there is gas actually that obviously needs to make place for that, so that is flowing down, so I have some kind of recirculation pattern here, so that all the gas will be able to make it there.
I want you to do something. So if some of these bubbles are coming down because
Yeah.
of that circulation, you should check the vectors here
Uh-huh.
to see if you really see a downward vector for, I cannot see it here.
Yeah.
Okay. Because that will help to just at least to verify that what you're showing is also associated with the gas stream.
Mhm.
Okay. There might be some assumptions there that you're not considering here, right?
Yeah. Or I can try to increase the number of velocity that I'm trying to plot. I only plot a very less number of velocity vectors. If I increase the number of velocity vectors, we can maybe observe the recirculation effect.
That's possible. I mean, it's also interesting to see here, and sort of in retrospect, it makes perfect sense, but I wouldn't have thought about it because of the small column size.
Mhm.
You break the symmetry in the beginning once, and now you're stuck, right? You have one big recirculation pattern here. You will never get a bubble on the right-hand side anymore.
Yes.
Right? I mean, you will always have a bubble fall on one side.
Right.
So that also clearly tells you this behavior is very likely not going to scale up. You have a larger reactor and that doesn't happen anymore.
Yeah.
Because you won't have these very large scale recirculations. Now you start getting smaller recirculation eddies around. So again, something for us to think about as we go forward and think about.
That's a
that.
very interesting observation that you should add to your thesis, actually, why you are getting bubbles in one direction. It's not always left or right, it switches, but then as it evolves, it stays there that way, right? But you're in a trap now, or you create that sequence.
Just like with that first, with the gallium case, right? And you have that initial instability that breaks the symmetry. And a bubble forms on one side, and it could be either side, but
Yeah.
once it has, the first bubble forms on one side, you're done.
Yeah.
That sets the system. Yeah, and then the other thing, the only other comment, well, I've one more afterwards, but it's slightly different, but, we have discussed that quite a bit, over the time, here that we're struggling understanding residence time.
Yes.
I unfortunately don't see anything about it in your thesis. That would be super important for us. Something that shows a plot for residence time versus flow velocity, like volumetric flow in the system for Gaussian medium, right? I mean, is it scaling in any way linearly with it? What's changing at these conditions? Because again, you have the effect that basically once I form a bubble, the bubble basically shouldn't know anything anymore about velocity beforehand, right? It's buoyancy that it differs things. Yet at the same time, the flow velocity, of course, has to determine the volume that I push through the system. So what ultimately then determines residence time? That's a really, really important question.
So what it takes to quantify residence time?
If I had more time, we could just watch the video and track individual bubble and as it coalescence, how long each bubble takes. But I was fully focused
You
on.
need to somehow make, you need to somehow define a methodology of your quantification, right? The kind of an average residence time.
Yeah, exactly. I just want to
Across-
say there isn't even sort of a clear, particularly when you have larger and smaller bubbles.
They
There's
are
a
absolutely
distribution
different.
of residence times,
Yeah.
right? So it might go beyond your time scale that you have left here, but it might help if you might sit down with Cornelius and explain to him how would you do it if you had time, so that he can take it over that and do it.
Yeah,
Because that's gonna be a really important. question
Absolutely.
for us. So I've one bigger administrative point overall. Your thesis is extremely well written. And I know you, and with all due respect, I mean, you gave a nice presentation, but that's not your voice, right? Clearly you used ChatGPT or something like that, which is fine. We don't have a rule against using it, but you must add a paragraph at the end of your thesis, which is say very clearly, I use ChatGPT version whatever 4.0 or whichever one it is. And I use the following prompts. This is what I did for this here, right? So as long as you are absolutely clear and transparent, that's perfectly fine, but you have to have this.
How frequently you use it?
Um,
I'm curious.
I write a paragraph, I put in ChatGPT to check the grammar,
What was your prompt?
rewrite this paragraph with perfect grammar and no mistakes in the paragraph.
That's very important, yes. Yeah, we already did check I use Identica or just checking, making sure that we are following everything. Because I knew that he's doing this, yeah.
Right,
But
I
that's
think the
standard.
same thing I do it, I do that standard by any document that anybody sends to me that I send it there. And that's another point, I mean, I'm wondering whether actually ChatGPT is almost trained by now to do this, right? Because if you run it through Authenticate, you can see that every single source is 1% or less. There is, and that never happens. I mean, if you write it as a normal person, there will always be a couple of sources that are 3, 4, 5%, because again, we all, of course, read up on, okay, volume of fluid method, how is it? And you read up in the source and then you sort of write it in your own voice, hopefully, but there's always something stuck over, right? So you always have some sources that stick
So
out.
what's the sorry, this is out of the discussion. What's the relevant? Do you know any? I know there's an email thread that you're exchanging. What's the relevance between? I checked that 1% or 1%, and you're right. That ChatGPT can communicate with all those references, right?
Sure.
It is communicating.
Right.
So what's the relevance between now plagiarism and using these LLM packages?
Well, I mean,
Is there any threshold here that we should be aware of, or?
you mean the percentage you have?
Yeah.
No, I mean, again, I have, I mean, as I said, the ACHE journal, of
Yeah.
course, every submitted paper is run through that.
Yeah.
And usually, I mean, we get 2 scores back. There's an overall similarity score, and that's very typically for most normal papers, proper papers, it's between 10 and 15%. And then there is the first source similarity, of course, right? I mean, sort of the one that is most highly cited. And if that is, if the, and that's completely individual. Unfortunately, we don't even have a policy against each job. But for me, basically, a warning flag is if a paper has more than 20% of an overall simulator score and more than about 5 or 6% of the first source, then I'm diving in. Then I'm going to go and look very, very carefully where it's come from. And very often you find it again, people, of course, have written a previous paper and the methodology of the method section, experimental setup or so, that a lot of that is copied. And that's fine. I don't, yeah, you don't have to be right. That's boilerplate stuff, right? But when you go in and suddenly you realize there are whole sentences in the results or what the conclusion section, yeah. That needs to be nice.
But there is no well-defined percentage that.
No, we have discussed it also, and it's difficult to find objective number. I mean, ultimately, it's sort of a gray zone, and the point is also not, hey, you have 23% similarity score, I'm rejecting your paper, but the only thing it does for us is, well, at least for me, I go in and I really now check, why is your score higher? And then you see again, if it's higher, like I said, if it's higher because of some boilerplate stuff or something like that, it's okay. It's higher because there is some content. If there is some content copied from their own stuff, then I may reject it simply because of lack of novelty results. If it's something that is higher because it's copied from somewhere else, then I check that.
Yeah.
Yeah, definitely, we're gonna add a statement and be more specific about exactly what counts for those sections.
I mean, again, it's sort of, I think as I said in my head, it's right. I mean, as long as you are transparent about what you're doing, you can do almost anything you want. Others might accept it or may not accept it, but you're basically not doing anything wrong, ethically wrong. But you need to be very transparent. Particularly, it feels like again, use of large language models, which is sort of still the total Wild West at this point here. Transparency is key. All that, some small points, but all the other major points we have touched upon already.
Do you have any other?
No, I see, I have, small, very minor edits and suggestions that I'm gonna send it to you and, email, very minor, though.
Thank you.
So.
Okay, Bala, so maybe you can leave the room and call you when you're done with that discussion.